is 3:05, so let's get started. So just a quick announcement, quiz 7 is out, due on Saturday as usual. And if you haven't started, it's actually very cool. It asks really fun questions about the things that we're doing, so I highly recommend you start that pretty soon. Other than that, I don't have anything, so do you have any questions about anything? No questions at all?
You're going to go over PDA right now, right?
Any other questions? Yeah.
If we have a quiz every week now, aren't you going to go over 10 quizzes?
Yeah, we'll probably hit 12 or 13, and the plan is to use the top 10.
Oh.
Yeah, that's our plan. We don't know for sure, because we haven't done this before, but we think there will be 12 or 13, so top 10. Yeah. Any other questions? Going once, going twice. All right. So, before all the fun of spring break and all that, what did we talk about before spring break?
PDA.
Yeah, these PDA things. What does PDA mean? Public display of affection? Oh yeah, push down on top of that. All right. My prediction is way off. Okay, well, what in the world is this push down on top of that? Yeah.
It's like an NFA, but it has a stack.
Right, it's just like an NFA, but it has a stack. So that's a nice and formal way of looking at it. So let's try to look at what the formal definition of it is. So if it's like an NFA with a stack, what do I need to define a PDA then? How many parts are needed for an NFA? 5. So how many do you think are needed here? 6, because it has the thing with the stack. So the PDA, again, has states like an NFA would. It has input alphabet. It has a transition function, start state, final states, exactly the same as NFA. But since we have a stack now, we need to worry about what can appear on the stack. So could I have a PDA where the input alphabet was the only thing you could allow on the stack? I mean, I could allow that, but could I have, say, whatever I can put on the stack alphabet is completely different from the input alphabet? Could I have that? Yeah, so there shouldn't really be anything barring us from putting anything we want on the stack. Could be the same as the input alphabet, could be different. So let's give another name to this gamma for stack alphabet. Okay? Well, we know most of this, or how at least it works. Set of states, input alphabet, just another alphabet, start state, final state. So all of those are pretty second nature to us. It's just the transition function is going to be a little different now because we have stack to work with. So let's figure out what the transition function is. Well, in the transition function of an NFA, what did we have for sure? Transitions between what? States. So what do you think the first component of this is? State. So I'm going to be in some state, and I will make a transition to another state, or a state. But now I got to decide, what am I going to do in terms of the input? For an NFA, am I allowed to not read the input at a given time? Yeah, and we denoted that by a what? Epsilon transition. So here, we can just say, oh, I could read something off of the input, or I can choose not to read something off the input. Right? I don't have to have something off the input if there's an epsilon transition there. But now we gotta worry about the stack, because we have things involving the stack, putting things on, taking things off. So what operations does a stack have? Push and pop for sure. What about, say, peek? I mean, I could say you can peek if you want to, look at the top element without popping it. But could I define it in a different way?
Pop it, then push it again.
Yeah, pop it and then push it again. So we can simulate peek using the operations we have. So I don't think I need anything other than pushing and popping. So we gotta really make an important choice right now. Can I do pushing and popping at the same time? At the exact same instant? No, because they're concurrent, different operations. So I need to decide which operation am I gonna do first. Do I do popping first, or push first, or could I interchange? So which one do you think I should do first?
Push first.
Could I do push first? Well, what if I wanted to pop later? I would pop the character I just pushed. What if I had a transition that involved popping and pushing? Which one should I do first? I think I need to pop first, because if I push first, then the character I want to pop now is on the second element right below the top. So I must pop first. Well, since now we're going to decide, now we could need to pop first, could I say pop nothing? Sure, let's make this as general as possible. So I can choose something from gamma, or I can choose not to pop and remind ourselves that this is pop. Here's a really good exam question, and actually was one at one point. Suppose I had a PDA which only popped on every single transition. What language does this PDA have? It'll be almost empty. Because what does the stack of a PDA start out as? Start out as empty, right? There's nothing on the stack when the PDA starts up. That's the convention. So if I have every transition pops, could I ever apply a transition? No. So what are the only possible languages I can have? I can never leave the start state. So it could either be empty set when the start state is not a final state, or it's accepting, in which case I accept the empty string. Okay? So I have to have this here. I must have not popping here because I need to be able to do transitions if I want to get the context-free languages, which I do. So I must have that there. But what is the output of this transition function? What has to be there? There must be a state there, right? Because I'm in a state, I apply a transition, I must go to a state. So the state must be there, no problem. But now I got to worry about pushing. Should I be allowed to push nothing? Yeah, just like I should be allowed to pop nothing, I should be able to push nothing also. And that actually will be very important when we do the other ones later. So that's nice. But what is missing from here? How many states can I go to once I'm in a state via this definition? How many states can I go to? I think I can go to exactly one, because I can only pick one thing from here. Oh, that's a problem. How can I fix that? Power set. Just like we fixed it for NFAs by including power set, saying I can go to any number of states that I want to, including 0. Let's make the same generalization here. And that will actually be very important as well. Okay? So, does everyone understand how this definition comes about? I assume you all do, so. But any questions up to this point? Okay. So, let's start making PDAs for things. So, here is a language I'm interested in, A's again, B's again, with n even. So it's not just n at least 0, I require n to be even as well. Please answer right. Is this language regular? No. What string should I pick? A to the, well, let's just be careful. If I pick A to the P, B to the P, what's the problem there? P could be odd. How can I fix that? 2P is fine. Another one you could do is pick the integer that's the even integer that's right above that, the closest even integer above P, but either one works here. Well, despite the fact that this is not regular, I want to make a PDA for it. And another great exam question. Suppose I had a PDA which only pushed and never popped. What is the language of that PDA? Or can I say anything about the language of that PDA? Well, if it only pushes and never pops, what is the way that a PDA could inspect its stack? It can't. The only way it could inspect its stack is if it pops. So since I said it never pops, it never looks at its stack. Do I need a stack? No, it only pushes on its stack and it never looks at its stack. So I might as well not even have it. So what is it at that point? Which means the language must be regular. So since that language is not regular, I can't just pop only, and I can't just push only. I have to look at ways of pushing and popping here. So we got to look at how to actually do that. So how do you think we can do this?
Would we keep a stack that keep track of like the number of A's you've seen and compare it to B's? Would we pick that part?
Yeah, so that seems like a sensible idea. Keep track of the number of A's and try to match it up with the number of B's. So in terms of the stack, it doesn't really seem that obvious. That seems like a sensible strategy, but it doesn't seem immediately obvious when you look at something like this that I can make a PDA for it. So let's make it slightly easier, and then we'll modify it. So let's relax the even condition and say n just has to be at least 0. Our favorite non-regular language, let's just work with that. And maybe if we can make a PDA for that guy, we can modify it for the thing that we're interested in. So how can I make a PDA for, say, this one? Well, let's see. If I have a string in this language, it's a bunch of A's followed by a bunch of B's. Right? Well, if they have the same number of A's and B's, is it true that each one of these A's maps to exactly one of the B's? Yeah, that seems pretty obvious. So maybe we can work with the stack that way. Maybe we can put the A's on top of the stack, keep pushing A's on the stack, and then once we get to the B's, what should we do?
Pop an A.
Pop the A's off as soon as we read a B. If everything matches correctly, then what is the stack at the end? It'll be empty. So that's nice. But do I have a way of checking if the stack's empty?
The stack symbol?
Right. I don't have a way of looking whether the stack is empty, so our technique is to put this special symbol right at the very beginning. And then therefore, the empty condition, once we get to the end of the B's, represents the dollar signs on top of the symbol. And that's our indicator that the stack is empty at that point. Okay, so let's start making a PDA for this guy. Well, what should be the very first thing I do then?
Read nothing, push down, $.
Yeah, so remember, the only times when I read are when I'm putting on the A's. As soon as I see an A, I put it on the stack. Whenever I see a B, I pop an A off and read a B at the same time. But here I'm putting that special symbol on the bottom. So it's not one of those two things, so I shouldn't read at that point. Should I pop or not on this transition?
No.
No, because the PDA starts up empty stack. So I'm going to pop nothing, and obviously I'm going to push a special symbol. I call it $, on the stack. I can use any symbol other than A or B because those are going to be interacting with the stack, so I just chose something else. And here, I could choose something different than the input alphabet anyway, so we're fine doing that. Okay? Well, once I get to here, what do you think I should do? I should be in the pushing A part, right? So as long as I'm seeing A's, I should push an A on the stack. Should I pop anything? No, because the only thing on the stack right now is $. I'm going to be pushing A's on, and I'm not at the B part yet, so I shouldn't pop anything. But where does the transition go? Does it stay here, or does it go somewhere else? Well, since I'm going to be doing this same operation over and over, I think I should just stay here. I think that seems sensible. So I'm just going to stay there. And as we just discussed, read an A, don't pop anything, and push the same character A on. So read an A, pop nothing, push a single character, the same character A. Okay? So now we're pushing on these A's, and oops, now we're at a B. So what do you think I need to do?
Pop.
Well, whenever I see a B, I need to pop an A at the same time because I'm trying to match them up. But here's the problem. Could I just stay in this state and loop on the B's? I don't think so, because if I just stay here, then an A could follow a B. And I don't want an A to be after a B here. So I do need to go to somewhere else. So your suggestion might be, let's just read the character B and pop an A off and push nothing because I don't want to undo the work that I just did. What's wrong with this? It's a valid transition, but is it what I want?
Don't you have to do that multiple times?
Well, I can come down here and do it. But what's the problem with doing that in relation to the language?
Doesn't catch n equals 0.
Doesn't catch n equals 0. If I come down here, I've read something, and that doesn't get epsilon the empty string. So how can I fix this? Well, I need to allow that possibility, so I'm going to have epsilon here. But can I pop then? No, I can't pop here. So I must pop nothing. And so purely my term, no one else uses this term but I. I call this a triple epsilon transition because I read nothing, pop nothing, push nothing. And all this really means is that I'm non-deterministically choosing the B part starts here. Okay? Nothing other than that. But any questions up to here? Okay? So what do you think the function of this state is going to be? Pop B.
Pop the A's.
Pop an A and read a B at the same time. And as we just discussed, I shouldn't push anything either. So read a B, pop an A, push nothing. Okay? But now, let's suppose I matched everything up. The A's were put on the stack, the B's were read, and were popped the A's accordingly. What is on the stack now? $, if everything matched up correctly. So the way we can check that is if we pop it off the stack. And then at that point the stack's empty. Should I read on this transition? corresponding to the dollar sign? No, because each of the reading transitions corresponds to putting an A on the stack or popping it off. But I'm not popping off an A here, so I shouldn't read. Here I'm going to be popping the dollar sign off. Should I push anything? I want to clean up after myself, right? I don't want to leave my stacks completely filled with garbage. So I'm going to be a good citizen and push nothing. But the key here is that stacks do not have to be empty when you accept. They don't have to be empty when you accept, but they must start empty. Okay? But here I accept all of it, obviously. Yeah.
For the last transition, will it only be taken if you can pop the dollar sign? Is that the case here?
Yeah, so it's saying that if dollar sign is on top of the stack, I can take this transition. I don't have to.
Even though it's epsilon transition.
Yeah, it's an epsilon transition, so for that reason, I do not have to take that transition if I don't want to. So PDAs are inherently non-deterministic, but for that reason, since there is a way for me to accept, I will take that transition. Okay. And any other questions about this? But this is not the problem that I want, right? I want n to be even. But here, I just set an arbitrary number of a's, at least 0. Oh boy, so how am I going to fix that? I must ensure that the number of a's is even. So is there an easy way I can fix this? Yeah.
Just add states on the A loop.
Right. So what we can do here is observe that the first time I get from the start state into here, how many a's have I read? 0. Is 0 an even number?
Mm-hmm.
I hope so. So this state in our mind should represent we've seen an even number of a's. Well, can I push or read multiple things in a single transition? No, because the definition says no, you can't. There's something called an extended PDA, which is used in a proof we'll do later in the Sipser book, but in the formal definition, I can only push or pop or read exactly one thing or 0 things. So I need to have another state. And that will represent, we've seen an odd number of a's. But how do these two states relate to each other? Well, even number of a's, how do I get to the odd one? I read one more. Should I pop on this transition? No. Should I push on that transition? Yes. It's just a mirror transition of what we had before. But now, I'm going to have 2 of them. So by the time I get back to here, however many times I go out there, I guarantee I have an even number of a's if I'm in that state. So that's nice. Do I need to do the same thing down here? I mean, I could, but do I need to? No, and why is that?
You're looping down there.
Right. The only way I can take this transition over and accept is if the number of b's exactly matches the number of a's. But in order to get down here, I must have had an even number of a's to start with, which means I have an even number of b's in order to accept, and the same number. So that's exactly what I want. Okay? Cool. That was a very simple modification, and we got the language that we want. Any questions about how we were able to make this? Yeah.
So the very last transition, that simply means that we can do an epsilon transition only when we see a dollar in the stack.
Yeah. That actually brought up an interesting thing. What if I had the string A, I'll do this. So this obviously is not in this language because it has a different number of A's and B's. But can I get to the accept state with this string? Well, let's see. I have to take this. I take 2 A's to get back to here, come down here, so there are 2 A's on the stack. I take this transition twice, so now there's nothing on the stack but $, and B left in the input, because I processed 2 of the B's. and I say, oh, there's a dollar sign on top of the stack, so I can take that transition over. But do I accept? No, why not? I haven't read all my input. So the really nice thing here is I can still come to the accept state, but I haven't read the input entirely. And that will be really important when we convert CFGs and PDAs in a second. But that's really nice that if we can't process the whole input, I'm stuck here. And, if I can't process the whole input, I can get to here, and I wouldn't accept. But if I could process the whole input and it's a bad input, I'm going to be stuck in here. So therefore, I get exactly the language that I want. Yeah.
What about the third B? If it's trying to pop an A, but an A does not exist.
I could remember PDAs are non-deterministic, so I could choose this transition or this one.
Oh yeah.
So I definitely can't choose this one. You're right, but I could choose that one. Yep. And actually, I'm forced to do that one. So cool. When we talk about deterministic PDAs eventually, which is actually what this is a deterministic PDA. We'll talk about how you are forced to do a certain transition or not. But PDAs in general are non-deterministic. Yes.
So the loop we had earlier for A, was that wrong?
No, it was the language when we had n at least 0, but I wanted to modify it for this one. So it's definitely wrong for this language, but it was right for the language we started with. The easier language we had. But any other questions?
And then we could add on the extra loop for B as well, right?
Yeah, but we could for clarity reasons, but it's not wrong to just have it like this. Yeah. Any other questions? Yeah.
Just to clarify one, the triple epsilon is just for the case of n equal to 0?
Yeah, that's the only reason. If I instead said that and n at least 1, then I have to do this. I would have to, yeah. Or I can do some modification here, but that would be enough. Any other questions? This is good.
Couldn't we fix having more inputs at the end by adding an extra state, where if we get an input, we just go to that state?
Again, these things are non-deterministic. If I come to here and there's an input left to read, then like an NFA, it'll just die at that point.
Oh, okay.
Right? So that's the really nice thing. I don't have to have every single transition drawn. So that's the really nice thing about non-determinism. Any other questions? This is like the best ever.
This is not related to
You have to speak up, sorry.
yeah, this is not related to this question, but we have seen that we need a PDA if it is a non-regular language.
If it's a non-regular but context-free language, yes.
Yeah, but if it is a regular language, can we do this stack?
We'll get to that question. An excellent question, we'll get to it. I promise. You have a question?
So for the transition here, transaction here, transition error. So can you kind of explain what they are? So the first one is the input alphabet, right?
This one?
No, just the symbols. So the first one.
Oh, yeah.
First,
Sorry. I know what you mean. So, first one represents what we read or do not read.
Okay.
This represents pop. This represents push.
oh, okay.
Yeah, I should have explained that. You're right. But that's the order in which you do things. You read, then you pop first, then you push.
Okay, thanks.
And for the example, you said AABBB, when we read the last B, and we have to pop A, right? But we pop it minus the dollar sign, but we have to put the dollar sign back, and then we read the dollar sign again.
I'm not sure what you mean.
For the last step, like you read an extra B, and now you have to pop A, and you find that it's not an A, it's a dollar sign.
So I think it'll help to trace through the computation. So here I have to go to here. I haven't read any of the input so far. I have A's to read. The only thing I could do is the transition out and back. So when I do that transition out and back, I'll process these two A's, right? And currently on the stack are two A's, actually, and the dollar sign. right? That's what's currently on the stack. Now, there's a B on the input, and the only transition I can take is this one, right? That's the only one I can take. Well, in this modified one, when I said n at least one, but it still works. So I have to come down here, which means I've read one of the B's, and I popped one of the A's, so that guy's gone. When I come down here, $sign's not on top of the stack, so I can't take that transition. So I must take this transition, which means I read a B, and I pop an A. And then here, I can either choose this transition or this one. I can't choose this one because A is not on top of the stack, right? So I can't choose that one. So I must take this one, which means I pop the $sign off, and there's no transition here out of this state. And so therefore, the computation dies because there's something left in the input to read.
So we have to check the stack, check the top of the stack first, and then decide which is the wrong line.
When we get to converting CFGs to PDAs, we may have multiple ways. So the nice thing is that that is handled by non-determinism. If there is a way to accept, it will take that way. Here, there was a forced choice. And in general, there's not usually a forced choice, but here we happen to have one. Okay? Any other questions? I'm ecstatically happy. But really, any other questions? Okay, so let's do this one. So it's slightly modified, extended a little bit. I ensured that the string W consists entirely of A's or is in the language we started with. Yeah, it's in the language we started with, and assume I kept it the way it was before. Okay? So, what do you think is an important part of that English description? Or. The word or. What do you think that corresponds to? Union. Oh, could I do union with PDAs?
Well, PDAs, they're similar to NFAs.
Right. So could I do union with NFAs and then see if we can modify that? How do I do union with NFAs? Yeah, two epsilon transitions to the two pieces, right? So maybe we can modify that idea. So I'll ask a very important question. It may not seem very important, but it is. When a PDA starts up, what is its stack?
Empty.
Empty, right? So let's think about this. I have a PDA right here and a PDA right here. They're expecting their stack to be empty. So first of all, should these two transitions pop? No, because if they did pop, then I can't even execute them, because this thing starts off empty. So that's good. What about pushing? Should I push anything?
$sign?
I mean, if I did push a character, then when I get to this PDA right here, its stack is not empty. And it's expecting it to be empty. Its behavior will change if I give it a different stack, possibly. So I must not push it. Because if I did, I will change, possibly, the behavior of the machine. So I will not push on these. Okay? Well, now we just got to make a PDA for the second part right here, and a PDA for the first part. Oh, we have a PDA for the second part already done. It's right here. So to avoid drawing that, and for the interest of time, I'm not going to redraw it. I'm just saying the PDA for that is right there. Is the one we just did. Which I can do because this is a theory class. So now, I handled the second part, now I just need to handle the first part. So can I make a PDA for recognizing strings that are just entirely A's? Can I do that? Yeah. Wait, is that language regular? I think so. It's just A star, any number of A's. Oh, how do I make a DFA or NFA for that?
If
Just have one state that's accepting and just loop on reading A's. Okay, so accepting state, loop on reading A. What should I do with the stack? Oh, yeah, go ahead.
For this, if we say consists entirely, do we not have to assume there is an A in there? Or?
Yeah, you can assume it's all of the characters in the string are A's. If you have the empty string, all of the characters are A's, right? Because they're 0. But what should I do with the stack here? Because I need to make a PDA for this. Should I pop? No, I should never pop. Could I push? I mean, if I push, that's okay because I'm never going to inspect my stack, but I'm going to be, again, a good citizen and not pushing. Oh, I think this tells us something very interesting related to the question I was asked earlier. For any DFA or NFA, could I make an equivalent PDA? Yeah, how do I do it?
Not push or pop.
Yeah, every transition, just adorn it with comma, epsilon to epsilon. Because a DFA or NFA never touches its stack. So the languages also, therefore, every regular language is recognized by a PDA. Which is nice. Yeah.
So in this case, when you start up and let's say that you read a B, in the non-determinism, like send that to a empty non-accepting state.
So remember that if there is a way to accept, it will choose that path. If there's a B, let's say whatever string it is, it starts with a B and is in the language. Well, actually it can't be because every string in the language starts with an A, right? Or is epsilon. But let's suppose I had a weird PDA that had a string in this language that started with a B. It will choose the right one, whichever it is. Whether it be this one or this one, it'll choose the right one because it's non-deterministic.
So if I try to feed in the string A, B, will it just not read it? Or how does that computation occur in this?
I'm not necessarily worried about the strings that are not accepted. Just like when we convert CFGs to PDAs, I'm not worried about the strings that can't be generated. All I'm worried about is the ones that do have an accepting computation. Okay? Any other questions? It may have a computation, but it may or may not have an accepting computation. Or it might not even have a computation either, so because it's not deterministic. Okay, we need to get on to the third question. And so this is where the real heart of the topic of PDAs comes up. So I have a CFG with start variable S and 2 variables. So I have this CFG, and I want to, and it says to convert it to a PDA. So how am I going to do that? Or how could I do that? Well, yeah, go ahead. Well, maybe we'll, do you have a suggestion? Well, I don't know in general if this language is regular though, so I don't necessarily have an NFA for it, right? If this was a regular grammar, I definitely could do that. But I want this idea to work for every CFG. Yeah.
We can make a PDA for A and then go from there.
I mean, we could make a PDA for A, but the problem is that when I'm working with the stack, if I enter the PDA for A with a different stack than is empty, then I may accept something else. So we'll always have to worry about the stack here. And that's actually one of the reasons why we'll eventually show that context-free languages are not closed under intersection. Because if I did a product construction type thing with as we did with DFAs, which does work, the problem is that the stacks themselves might conflict. Because if I have this, a stack in this state and a stack in this state in a different PDA, then they may conflict if I do the product construction on them. So but that's essentially why they won't work there. But what is a general way I can do this? So one thing we know about CFGs is what do they have with respect to strings? It starts with a D and ends with derivations. They have derivations, and in particular leftmost derivations. So what does every derivation of this grammar start with? Has to. The derivation. What thing has to start the derivation? The start variable s, always. And that will actually be very important. Everything today is important. I don't know why. But, well, I should do know why, but anyway. Let's just say I'm going to apply the rule s to 3a's. So it's going to be replaced by 3a's. And since we're talking about derivations, I could replace any one of these that I want to, but I'm going to emphasize that we talk about leftmost derivations because that'll, again, be extremely important to this. It won't work unless I do leftmost derivations. So I have to replace this first A, and let's say I replace it with VACS. So let's say I replace it with VACS, and I have the two A's afterward. And let's say this A, which is the first one, obviously, the leftmost one, I say that that one goes to empty, so it drops out. And let's say that S is going to be replaced by the other rule, AA, GC little a, big A, with two A's. And then just for simplicity, let's say that all three of these A's are going to drop out with epsilon. So BCA with two big A's, BCA with one big A, BCA with nothing afterwards. And I can't do anything else here because I have a string full of terminals. So that's good. Well, this is a leftmost derivation of that string. Maybe we can use the stack somehow to model the derivation as it's happening. So the derivation starts off with S, so maybe we can put that on the stack. And then, does S get replaced by the three A's, or does something else happen? Does it get replaced? Is S right here?
No.
I hope not. So S is going to be replaced. So what do you think happens on the stack right here? It pops in. So it's going to get X'd. Then I got to push those three A's on. So let's say that I apply that rule and eventually get three A's on the stack.
Leftmost A on top.
We'll get to that in the very next one. Okay, well, now I gotta think, well, it seems like this top A is gonna get replaced because I can't access anything other than the top element of the stack. So let's say that that element gets killed off. So I have two A's on the bottom, and then I replace that top A with BACS. But what order does that appear? What thing is on the top of the stack now? Or should be? It's going to be B. Why? Because I'm processing this left to right, and so therefore, since I'm doing leftmost derivations, the leftmost variable must be near the top of the stack. And another thing is that since PDAs have an input, they process them left to right, so I need to process the things on the stack in the same order. So I must push this way, right to left. So the first thing I push on is big S, then C, then big A, then little b. That's my stack now. Oh no, there's not a variable on top. There's a terminal on top. What am I going to do? Woe is me. What am I going to do? Pop it. And what else am I going to do along with that? Read it off the input. So the terminals I'm going to produce, remember, in the derivation, the terminals never get replaced by anything. So when I put them on the stack, they're never going to be replaced by anything. So therefore, I can just read them off the input. And if I've read all the input and there's nothing but the $sign on the stack, I should accept. Because if there was a variable on top of the stack, I would have applied a rule to it. And if there was a terminal, it would have been produced because of non-determinism. So that's exactly what we're going to do. Apply a rule in reverse order on top of the stack. If a variables appear, I apply a rule. If a terminal appears, read it off the input and pop it at the same time. Okay? Does that seem like a good idea? It's the one that works, but does that seem sensible? Okay. So let's try that. So what is a major problem with doing this blindly like this? What's something that might happen?
Are we assuming that every string we have is integrable?
I can't assume that. It's the ones that have an accepting computation in the PDA. Other strings might not have an accepting computation. So, what's the problem that might happen in terms of the stack? What might you pop? What type of stack might you pop? Starts with an E and ends with empty. Right? I might pop an empty stack with a string that's not in the language that I want. So how can I safeguard this? The bottom of stack marker, just like we did with the other examples. So that's what I'm going to do here. So I'm going to put a bottom of stack marker at the very start. And once I've read all the input, if I've matched everything correctly, the $sign's on top of the stack. And how do I know I'm done? The $sign's on top of the stack, so I pop it. Okay, well, let's make a PDA then. What should be my very first thing to do? Push a $sign. So I don't know if I'll have time to do the whole thing. So I'm going to push the $sign on. Maybe I'll just do something like that. Is there a variable and or a terminal on top of the stack right now? No. Oh, I can't apply a rule or do anything. What do I do to fix that? How do I get something that I want at the very start on the stack? I should push what? The start variable. Because every derivation starts with a start variable. So since I'm modeling derivations with the stack, I push the start variable. So I'm going to have another transition, epsilon, epsilon, 2s. Okay? So now we have two choices. Well, not choices, but two possibilities. Either terminals on the stack, or variables on the stack, or eventually the $signs on top of the stack. I won't worry about that. If a terminal's on the stack, what do? I read it off the input and pop the same or different character. Same or different? Same. Because I want to do exactly what the input has. So I'm going to pop and read the exact same character. Well, the terminals in this grammar are little a, little b, little c. So I'm going to have 3 transitions for each of them. Well, 1 transition for each. And since I can do that in 1 transition, I'm just going to self-loop back and then try again. Because there may be another terminal on top of the stack eventually. But now I have to apply, I got to change the rules into a bunch of transitions. So let's do the, since I only have time for one of them, let's do the long one, A to BACS. So here I'm saying A is on top of the stack, and I got to push this right-hand side on. So what order should I push everything on? Right to left, just like we said. So the first thing I push on is S, then C, then A, then B. Okay, well, can I push all 4 of those things and pop A in the same transition? No, because I can push or pop at most one thing. So I can't do this in a self loop. So I'm going to come out and then eventually come back. So since this transition and the other ones, including pushing, have nothing to do with the terminal on top of the stack and popping it off, none of the other transitions will read. The only transitions that will read are these self-loops. So here, this transition won't read. I said variable A is on top of the stack. It needs to be replaced. So I need to pop it off. And here, I'm going to push nothing. I could push S here, but I'm going to suggest something that you separate the part which represents popping the left variable and separating the part with pushing the right-hand side. I could put it here, it won't change anything, but it's just a mindset to get into it. So now I gotta push the right-hand side of this guy from right to left. So here I gotta not read, not pop, and push an S first. I gotta then push a C. I gotta push an A. Then I gotta push a B. Then I triple epsilon back. And then I know what some of you are thinking. You could delete this transition and make this B transition come back. That'll be fine. But again, I want to separate the part which represents popping the left character, pushing on the right-hand side, and the state that does the terminal part. Okay? And I definitely don't have time to do the other ones, but let's just assume I did the other three rules. What do I do now? Or am I done? Let's assume I did those three. Am I done? No, there's no final state, so the language of this is empty. Well, how do I fix that? If the string was produced, I read the whole input, what's on the stack now? $. So I need to go out on reading nothing, popping $, and pushing, well, whatever, to a final state. Okay. Any questions about this whole conversion? Again, you have to have one of these going out and coming back for every single rule, but I just did one here. Any other last questions? All right, I'll see you next week.